We were talking about the useful energy, okay? And we said that we can compute it from, so Q that is useful, okay, is equal to the absorbed energy, Q absorbed, times the efficiency. So it's Q absorbed. And what is the absorbed energy? They gave us the flux, the absorbed flux per unit area, and they gave us the total area, okay? So the rate of absorbed energy is equal to the area times the flux, okay? So here we have Q times efficiency. Now Q absorbed is the area times the flux of energy, rate of energy hitting the solar collector, which is 500 watts per meter square. So here from units you can know what to do. So here you have 20 is in meters square. You should multiply by the incident rate, which is 500 watt per meter square, and this will be the absorbed rate. Now the rate that will be used to heat your water is only 80% of this part, since they said that the solar collector efficiency is 80%. This means that the 20 other percent will be lost. So now we have Q useful, okay? We can calculate it, we have everything. Now, to continue, they want us to find what is the time needed to heat 1,000 liters of water. So to be able to do that, we should write the relation between Q useful and the amount of water heated, okay? And you know that here, heat is transformed into what? So the heat absorbed from the solar collector is transformed into sensible energy to heat water. And when we heat a certain fluid and its temperature increase, so we are in the not in during phase change of the material, then what will be the formula which will give us the amount of heat absorbed? It will be m dot. So it's m dot Cp delta T. Okay, it is m dot Cp delta T. So I will write it here, m dot Cp delta of temperature. Now, they gave us, they didn't, if you want here, m dot is not given, okay? But I can calculate it because I know everything, but I don't know m dot. I know the specific heat of water, it's given. And even if it's not given, I can get it because it's a constant. Yani for a certain interval of temperature, I will neglect variation of then Cp, okay? And Cp of water in this range of temperature is known. And here it's given to be 4 times 10 to the power C 3 joule per kilogram Kelvin. So all I have to do now is to replace Cp by its value. And what is delta T? Delta T is the difference in temperature between the outlet and inlet condition. So I will write that I have it equal to m dot, which is unknown, okay, times Cp. I will replace Cp by its value, which is 4,000 joule per kilogram Kelvin, okay, and I will also multiply by delta T, which is the outlet temperature 333 minus the inlet temperature 293. So from this relation, okay, what can I get? So I calculate m dot, which is the only unknown, okay? So I can calculate m dot. And since I need the time, I need the time needed to heat 1,000 liters of water, then instead of m dot, I can calculate what? The volumetric flow rate, Q dot, okay? Because Q dot is the volume heated over time. And since I have as input volume, it will be more interesting to find the Q dot, okay? But we know that m dot and q dot are related, okay? Because once I have m dot, what can I say? I can say that the volumetric flow rate that of water that can pass through my collector is passing through my collector is equal to m dot over rho, the density of water, okay? Because you know that mass is rho times the volume. So from here, I can calculate the value of Q dot, and Q dot represents what? Here it's a constant, because it's a constant here, okay? I am working in steady state operation. Then I can say that Q dot represents the volume that is of water that is heated over delta T, okay? Over delta T, okay? So I can say here that since they asked what is the time needed to heat 1000 liters, which correspond to 1 meter cube, okay? So for V equal to 1 meter cube, for V equals to 1 meter cube, the time needed to heat this amount will be equal to delta T is equal to Q over to V over Q. Okay, delta T is equal to V over Q, and I replace V by 1, so I can get the time needed to heat my water. Okay, any question on this problem? So this is the type I expect you to know how to solve. Okay, so you go from simple formulas, and just from the question you see what are your unknowns, and you put the corresponding equation to find your unknowns. Another example of problems that you can have, this is an example on photovoltaic system. So assume that 1000 watts per meter square of solar radiation is incident on a solar panel of 1 meter square that converts 10% to electricity. If you remember, when we talked about photovoltaic systems, we said that one of their disadvantages is that the efficiency in producing electricity is not very high. But on the other hand, we have a very high percentage of converted to heat. And we said that if we can benefit from this heat, then the efficiency of our system will increase in a significant way. Okay, and this is a problem showing this application. So assume that heat transfer coefficient of 12 watt per meter square Kelvin is effective on both sides of the panel. This, you know that when you have a solid and you have a fluid going over it, the main mode of exchange of heat between the two is the convective mode. Okay, so we can say that heat is transferred from the panel towards the atmosphere by convection, and this heat is calculated as HA delta T. Okay, so the question is, assuming that the ambient air temperature is 20 degrees and the PV surface temperature at steady state is 53 degrees, then what is the efficiency of the combined system? Okay, so here, if you want, what we have here in this system, we have a PV panel. Okay, and this PV panel is able of producing, if he receives, let's say, from sun 1000 watts, 10% of this energy, of this power, will be converted into electricity. So let's say for 1000 watts, we are doing the analysis, of course, per meter square. Okay, so they said assume that you have 1000 watt per meter square. So here all the analysis will be for 1 meter square. So if you have a larger area, all you have to do is to multiply by the corresponding area. So for 1000 watt hitting my PV system, I have 100 watt converted into electricity. Okay, now concerning the amount of heat transfer, how we can compute it. Okay, they said that the ambient temperature is 20 degrees. So here your panel is exposed from one side to the atmosphere. Okay, so from one side, it's from the external side, if you want, from external side, it is exposed to atmosphere. And here, to profit from the energy, the heat released, what we can do from the other side, at the back of the PV, we can pass a certain air flow that can take heat. Okay, so for the external side, we cannot do anything because heat will be lost. But for the other, from the other side here, we can pass, let's say, a flow of air. This is what will happen. Let's say we have ducts or a certain system that is where we have air passing through at the back of our PV, and then let's say it will get inside the room, for example. Okay, so this heat will be transferred to the air, to a flow of air that can be used for heating purpose. Okay, so now what we want to calculate is what the heat transfer between the PV panel and air. So as we said, in general, between a solid and a fluid, the main mode of heat transfer is convection. So what we can write is that Q for each side, Q from each side, and here I'm talking about power in watt. Yani if you want, we can say it Q dot. Q dot, I mean per unit time, rate per unit time. Okay, because you know that when you do HA delta T, you obtain a power in watts. Okay, so for from each side, the energy, the power exchanged is HA delta T. And here they gave us the convective coefficient, which is 20. They gave us, sorry, 12. It's 12 watt per meter square Kelvin. We should multiply by the area of the PV system. Here we are doing the analysis for 1 meter square, so A is 1, times delta T, which is the temperature difference between the PV surface and air. And of course here the exchange will be from the PV towards air since the PV surface is hot. So it's times 53 minus 20. So nearly it's equal to, if you do the calculation, it's nearly 400. Okay, so what we can say here is that from each side we have 400. So but the thing here is that the side from at the level of the atmosphere, we cannot benefit from this heat because it will be dissipated into the atmosphere. On the other hand, at the other side of at the back of the PV system, where the airflow that is moving can be used again, can be reintroduced into the space or used for any heating application, will be useful. So this is why we will say that the heat from the external side is lost. So heat lost to the external side will be 400, while heat transferred to a flow of air that can be useful is also 400. So in total here, until now, we have 900 watts. So what will happen with the remaining part? You know that in general, not all the fraction incident on the panel will be absorbed. Okay, so here the remaining part is reflected. Okay, so the remaining part is reflected, and of course it will not be used. So in total, what are the useful amount of in watt? What is the useful amount in watt in total for this system, for the combined system of
100.
Yeah,
100.
exactly 500, because the useful part is the electrical part and the heat delivered to air, which will be used for the heating application. So this is the useful part in the problem. So this is the useful part. So now in total, Q useful in total, so useful power, Q dot useful is equal to 500. So now if I want to calculate the efficiency, so it's 500 watts per meter square. Okay, so of course now to calculate the efficiency, I can say that the efficiency is equal to the useful power over the total one received, which is 500 over 1000 equal to 50%. So you see here what is the advantage of the combined system. If you use only the electrical application, what will be your efficiency? So if I just take the electrical application, the efficiency is 10%. So it will not be worth of going for PV. But when I combine PV with another system to profit from the lost heat, then I can increase the efficiency of my system from 10% as electrical efficiency to 50% as combined efficiency when I combine PV and heating system. Okay, so
Miss, how did we calculate the heat loss to the exterior?
heat loss to the exterior is equal to the heat transfer to air, because look, the PV has two sides. One exposed to the external atmosphere, so here you cannot take the heat, and it will be dissipated. Okay, so because the area is the same from the two sides, so this is your area, it's the same from the two sides, and the temperature of air here is given to be the same as from the atmosphere level and from the backup level. Okay, so since we have same area, we have same H and same delta T, so Q lost to the atmosphere will be equal to Q lost for air going on the back of the PV system. Okay.
Yeah, the air at the back of the PV system come in 20 degrees.
Yes. Yes.
Okay.
If not, they should give you what is the temperature, and if you have different condition, they should tell you that at atmospherical level you have 20
This
degrees, let's
temperature.
say, and at the backup you have another temperatures. I can tell you this, so you will take a different temperature for each. But since here they specify just one temperature, and you know in general what they do, in general they draw air from the atmosphere. This is why they have considered the same temperature. But you cannot draw air from the upper side. Why? Why you should take it from the back side? Who will tell me why we don't blow air from the upper side to take energy also from this side? Because this will affect the solar energy absorbed. Okay, so from the atmosphere side, I cannot do anything because I want to benefit to the maximum from solar energy captured. So I will only take heat from the back side of the PV system fan. Okay. Other question on this problem? Okay. So now we'll continue with the last problem. And this is a big problem on chapter 8, the economical part. So here in this problem, we will repeat, if you want, all the concepts we have learned in the economical chapter, in the economical analysis chapter. So we have the lifetime of a 3 kilowatt wind turbine is 20 years. The initial capital cost is 2,000 euros per kilowatt, and the yearly maintenance cost is equal to 2% of the capital cost. The salvage value of this turbine is equal to 400 euros. The turbine generates 7,500 kilowatt hour per year. The selling price is 0.13 euros per kilowatt hour for the first year, 0.12 for the second year, 0.11 for the third year, and 0.1 for the remaining years. We have three questions here. First, we want to determine the rate of return on investment. Second, we want to find the discount rate for a payback period of 10 years. And finally, if they gave us the discount rate equal to 5%, we want to determine what is the discounted payback period. So we will do together the analysis of each term in the given to see how we will use it. Okay, so I will open a new file and we will solve on the file together. Do you see the word file now? I opened.
Yes.
Okay. Now, I will go first to our PowerPoint to remember the main formulas we have seen together for the economical analysis. So for the economical analysis, you have the life cycle cost. Okay, the life cycle cost will assess, if you want, the total costs over the whole lifetime of your system. Okay, so here the formulas I will need here in this problem are these two, so let us take them. This one first can give you the life cycle cost, and you can assess it for the whole lifetime period, or you can assess it until any year end. Okay, so it depends if you, for example, if they ask you what are the benefits at year 5, you can calculate what is the life cycle cost until year 5, and then you should compare incomes and if you want the costs to determine if you have a profit or not. Okay, so this is the first formula we will use. We have also that when we have a constant discount rate, we can use the geometrical formula here to simplify the analysis and simplify the calculation, this one. And we will see how to use it in this problem. Okay. So these are these are two important relations we will use. Now, concerning also the we have something new here that was not introduced in the chapter. I will explain it now. Do you have an idea what is the salvage value? When we say the salvage value of this turbine is 400 euros, this means what?
When we sell it after a certain amount of years, we sell it at this price.
Exactly. So when your system will not operate anymore at the end of the lifetime, you still have maybe some pieces that still work, so you can sell them. Okay. So at the end of the lifetime, you have a certain small income due to selling the remaining parts that still work. This is called the salvage value. Okay, and we will see how to use it in the calculation. And of course, another important relation to use is the one when we want to assess the profit. Okay, the profit which can be assessed through the net present value. Okay, so here in this before the net present value, this will give you this formula in the course if you want. Here you have in detail how to use the salvage value. Okay, the salvage value will only be used at the end lifetime of your system. So if you are doing the analysis for a year different than the final year, you don't include the salvage value. Okay, so I will also take this relation and we will and do the analysis of it in the problem. So you should be familiar with
Doctor?
this. Yes.
This formula wasn't included in our slides.
Yes, because you know why? Because I will because I will explain it in detail in the problem, because in this way you can understand it better. This is why I didn't include it. Okay, but now I will include it and with all details. Okay.
Okay, thank
you. Okay. And for the net present value, okay, for the net present value, this is how we assess it. It's the summation of the incomes minus the life cycle cost for a certain year n. Okay, so let us see how to use these formulas to answer the questions of this problem. Okay, so first, to begin with, we should look at every number in this question is used for what. Okay, first they said we have a 3 kilowatt wind turbine for which the lifetime is 20 years. So first you can say that n in this problem is equal to 20 years, which represents the total lifetime of the turbine. Okay, so this is equal to the lifetime of the turbine. Now, the initial capital cost, it represents what? This is the investment. Okay, so I is the initial capital cost, is the one you put before doing anything, and before starting your project. You cannot start your project before putting this amount of money, okay, to buy the equipment, to buy the land, etc. And all you need to have your project ready. This is the initial capital cost. Here for a turbine, for example, this is the price of the turbine. The initial capital cost constitutes the price of the wind turbine. And here they said that the cost is 2,000 euros per kilowatt. So since the turbine used is 3 kilowatts, then what will be the cost? It will be 3 times 2000, because our turbine is 3 kilowatts and the cost is 2000 euros per kilowatt. Okay, so we deduce that the price of our turbine will be 6000 euros. Okay, so equals to kilowatt will be simplified, and the initial cost is 6000 euros. So this is the initial investment. Now, the yearly maintenance cost is equal to 2% of the capital cost. So what is the maintenance cost? You know that each year we need to check our system to see if something is not working, if all is okay. So we need a certain cost. Here, they assume that this cost is constant over the years. So here, if you want, it represents this term in the formula. Okay, because when you assess the costs, you have two parameters. You can have maintenance cost and you can have operational cost. Okay, maintenance cost, it means, as we said, if something will not work, we should fix it, etc. Operational costs, sometimes you need, let's say, if not for a wind turbine, if you have another example, let's say you need a backup system, so you need to use fuel with it, for example. So you need to provide an additional cost. Here, for a wind turbine, we only have maintenance cost and no operational cost. Since we don't need, here, they said, they didn't mention that we need any auxiliary system or any other operational cost to use. So in this problem, no operational cost, we only have maintenance cost. But in some problems, I can tell you the operational cost is like this, the maintenance cost is like this. This means you should add the two. Okay, so always in the cost you take into account two things, operational and maintenance, and it depends on the problem. Sometimes maybe they will tell you no maintenance cost, only operational, so you will cancel the second term and take into account only the first, or you can have the both at the same time. Okay, so here the maintenance cost is very important in assessing what? In assessing the life cycle cost of our system, LCC. Okay, so when we want to yes,
I'm sorry، بس ال CNF بال LCC هي
salvage value. Yes, yes.
عم نشيلها من الكوست لأنه we are selling it back يعني بعدين.
Yes. Why
do we have
in the life cycle?
نعم. السالفج منا بالsummation, right? السالفج بدها تكون at the end of the cycle.
Yes, منا بالsummation.
Okay.
No.
Okay.
يعني you have this in the life cycle cost. You have the initial investment, which is the initial cost of your system. You have with years, each year you have operational and maintenance costs, so you should account for them. But as we said, with time, the value of the money and will change. And what you can buy now with $1,000 is not the same what you can buy from 10 years. So this is related to the confidence in future. So we say that with time, if you want what was worth, let's say $1,000 from 10 years, okay, is now will worth more now. This is why here we call it in this calculation we refer everything to the initial state. Yani by dividing by 1 plus a to the power I, we assess the value of the money at the initial year of investment. Okay.
Yes.
This is why at each year we divide by 1 plus I, a to the power I. And more you go in time, more the value will decrease, because due to what we said, that with time you have always confidence factor. So you will consider that if I am very confident in my country, let's say, I can say that if I take A0, this means I will consider that my money will always be able to, the same amount of money will always be able to buy the same things. So I am very confident in this case. And when we do the analysis of a project, it's not recommended to put A0, because you always have risks that you cannot for example, the coronavirus, no one can expect it. So even if your economy is is one of the best in the world. Sometimes you might have risks that are not predictable. This is why you should always, to be on the safe side, we should take a high enough, in general, a value of 10% would be okay. Okay, even if we are in a country that is safe, sometimes we should pay attention that some risk can be introduced. So the second term, so if I want to write here in the life cycle cost, I have first the investment. This is the first term. I have for each with time, I have each year operational costs and maintenance costs. And it depends on the problem which one is zero, and sometimes both can be at the same time. Okay, and at the final year, so if I'm calculating the life cycle cost, the overall life cycle cost from the starting to the final year, I should subtract at the end the value, the salvage value. Okay, and for the salvage value also I should divide by 1 plus a to the power n, because as we said, value of money will not be the same with years. Okay, so this is the total life cycle cost prediction. Now, in this problem, they gave me the salvage value. So this is C and F is 400 euros. So I can replace it by 400 euros. Now, for the discount rate, it's not given. So I have several questions, and in each question, I have different conditions. So A is not known, and we will see how to calculate it depending on the question. We have N is the lifetime of the system. It's given to be equal to 20. Now, concerning the initial cost we have calculated together, it is 6,000. So also we have it now. So we still have to compute the operational and maintenance cost. They said they didn't mention anything about operational cost, so we will set it as 0. We only have maintenance cost. Okay, and for the maintenance cost, they said that if we go back to the given, so maintenance cost is 2% of the capital cost. So I can say that maintenance cost CM is equal to 2% of I. This is the given. Okay, so 2% of I. Okay, so if you want, it's 2I over 100, which is equal to 120. Okay, it's 120 euros per year. So this is the cost per year. Okay, per year. Now, the turbine generates 7,500 kilowatt hour per year. This information is very important. Okay, it is true that we said that the turbine used is 3 kilowatt, but no one will tell me that it will operate continuously over the whole year. Okay, so always they should give me the time, or they give me the number of hours of operation during the year, or they can give me the total energy provided. This is what they did. They said that the turbine generates 7,500 kilowatt hour per year. Okay, who can tell me now how much hours then it will operate?
We do
number by the number kilowatts per hour.
Yes, we divide. You can say that if you want here, they gave us the total energy, okay, provided per year. So the wind energy per year, the wind energy, this wind energy per year is the income, if you want, is the income of your system. So the wind energy per year is equal to 7,500 kilowatt hour. And this means that if they ask for the number of hour of operation, so if I want to find the number of hours of operation, it will be equal to 7,500 over 3, because it's in kilowatt hours. The energy is given in kilowatt hour, and the power is in kilowatt. So if you divide the number of kilowatt hour per kilowatt of the turbines, you can get the number of operational hours, okay, per year. So this is the number of hours of operation per year. Okay. Since they directly gave me the energy, it's fine. No need to know the number of operation. Sometimes they, instead of giving you, for example, the total energy, they just give you the number of hours, and knowing the power of the turbine, you can deduce the total energy delivered. Okay, by multiplying 2,500 by 3 kilowatts. Okay. So now, the second step we will do is that we need to continue the analysis of the given. The selling price is 0.13 euros per kilowatt hour for the first year, and 0.12 euros per kilowatt hour for the second year, 0.11 for the third year, and 0.1 for the remaining years. And in general, why we do this strategy? We start by a high selling price, then we reduce it with time to increase the profitability of the project and reduce the payback period. And in this, and the role of the government is very important in such projects, because as you know, this cost might be high relative to maybe fuel consumption, electricity. But if government force the population to use it, then it can establish the project and help renewable energy in starting. And once it will start, with the development and technologies, the selling price is reduced. And this is what happened in Europe, for example, or in the United States. So now it becomes a very viable system, and they reduce a lot the consumption of fossil fuels. Okay, so now, since the cost, the income, if you want, per year is changing, here we should pay attention in the calculation, and we will see together what to do. Okay, so the first question, so let me start now with the first question and see how we will deal with this information here, how we will use it. Okay, the first question, if we go back to the slides, was to calculate first, determine the rate of return of investment. You remember what was the definition of the rate of investment? Who remember?
Yes, it's the discount rate at which you obtain an NPV of 0 after the lifetime.
Very good. So the NPV, the ROI, or return on investment, okay, represent, it is the discount rate. By definition, it is the discount rate for which the NPV, which is the net present value, becomes zero at the end of lifetime of the project. Of course, in general, we should have, if you want, A smaller than ROI, because if we just have a zero balance at the end of lifetime, it's not profitable at all. Okay, so but in order to see what is the risk we are taking, a good index is the return on investment, because if the return on investment, if the value of A is very high, this is good,